Greetings and salutations. My name is Elena Becerra, and here with me today is Brittany Russell, Erica Takara, and Fabiana Mago. We are Group 7, and in the following slides, we will be presenting to you all the production of insulin through a chemostat. To begin, we have an introduction on a chemostat reactor. Chemostats are essentially CSTRs, or better known as a continuous stirred tank reactor, where a fresh medium is continuously fed. They also have monitor equipment and pH controllers to measure and keep an optimal environment for the cells to grow. The cells in the reactors are reproduced and removed at a continuous rate. An important characteristic of chemostat is that operators can easily control the cell growth rate by modifying the volumetric feed rate, which is dilution rate. E. coli is selected as our microorganism, since it is known to be preferred for large-scale production. As a scale time, there is sufficient background information about this bacteria as to understand its optimal conditions to maximize its production. One main advantage of using E. coli is a short doubling time that this bacteria has. Under rich nutrients, environments, and controlled conditions, it is possible to obtain a doubling time of E. coli as quick as 20 minutes.
Our desired reaction has a substrate containing all the nutrients required, such as nitrogen and oxygen, for our cell growth. The desired product consists in the amount of cells produced, that later we go through a purification process to extract the insulin contained in them. Acetate is presented as a side reaction during the E. coli growth in the presence of carbon dioxide. Additionally, acetate is segregated by E. coli during growth. It is empirical to minimize the formation of acetate since acids inhibit the growth of cells and causes instability in intracellular proteins. The temperature used was of 37 degrees Celsius with a pH of 6.8. The nutrient limiting was our glucose, and the catalyst used was TPI1. First, it was found an experiment of insulin production, using E. coli as a host, performed in a batch reactor. From this source, it was possible to obtain the optimal conditions required for E. coli culture, as well as the glucose consumption at several time intervals. With this data, further calculations in a batch reactor were performed to later transfer into a chemostat. Required adjustment and scaling were performed in order to meet the desired daily production.
When working with chemostats and biological organisms, there are some safety factors that should be taken into consideration, such as work exposure to chemical waste and the potential exposure to microbe strains during equipment operation and maintenance. Additionally, microbes may become airborne, which can be inhaled or ingested by the worker. Some safety controls that can help mitigate these safety factors are the use of personal protective equipment, PPE, and the installation of ventilators and air handling systems. These are the equations we use for our system. We have the mass balance for the cell and the substrate, where Cc would be the concentration of the cell, Cs is the substrate concentration, Rg is the growth rate, and Rd is the death rate, which is negligible since the growth rate is much larger than the death rate. The dilution rate can be expressed as V0 over V, or the reciprocal of the spacetime. The rate law was modified using the Monod equation, where Ks is the Monod constant and mu max is the maximum specific growth rate. In addition to a steady-state system, we assume a well-mixed reactor and an incompressible fluid. On this slide, we have a general energy balance where we assume the Shefty work to be negligible and the energy term related to the cells entering the reactor was assumed to be zero since the cells are previously fed to the chemostat. The enthalpy and the Gibbs free energy for the E. coli were found to be negative 137.38 kilojoules per mole and negative 60.91 kilojoules per mole, respectively.
Data modeling approach. The modeling approach for our system was based on experimental studies performed in a small-scale batch reactor and chemostat. We first extracted data for the cell and substrate concentrations associated to the cultivation time. Additionally, we recorded the dilution time. We used that data to fit into the Monod equation. Using linear regression, we obtained the kinetic parameters needed, the Monod constant, and the maximum growth rate. The growth rate of the reaction was found using numerical derivatives of 3 points. Finally, we used these values to scale up to an industrial size. In this slide, we will be discussing our results. After following the approach just described, the maximum specific growth rate was found to be 0.3993 minutes inverse, and the Monod constant was found to be 3.1405 grams over liters. After the output for the chemostat was calculated with the equation shown, where X subscript M corresponds to the maximum biomass concentration, X subscript 0 corresponds to the inoculum biomass concentration, T subscript A represents the delay time between successive exponential phase cycles in the batch culture, and T subscript D the fastest doubling time. Finally, the output for the chemostat was found to be 465.5 grams over liters. With the desired output concentration and desired exit mass flow rate of 2,000 tons per day associated to an industrial production, the volumetric flow rate was calculated. As the dilution rate was known, the residence time could be calculated as the inverse of the dilution rate. Therefore, the volume needed to produce the 2,000 tons per day could be calculated and was found to be 451,230 liters. In this slide, a graph of the yield of cell growth over the substrate consumed is shown. This was calculated to understand how many grams of cells per volume were growing from the change in concentration of the substrate. Over a period of 14 minutes, the ratio of growth changed linearly from 1.6 to 3.2. Conclusions of this project were: including a batch reactor for initial cultivation before a chemostat for insulin production allowed the group to scale up the chemostat and determine the volume necessary for an industrial production of 2,000 tons per day of cells carrying insulin. Due to fast time of reproducibility, the E. coli demonstrated to be a good microorganism to produce insulin. Thank you for watching our presentation and have a great day.